Hi, good afternoon and welcome. So I'm going to offer some thoughts on quanta and interpretation of quanta based on light, and also some implications for quantum computing. So just as a little background, last year at this conference, I had presented a model of light. And so I'm going to quickly go through that model and then basically dovetail into a discussion of quanta and quantum computing. So just as a summary, this looks a little complex, but this is how I represent light mathematically. And I'm going to break it down over the next few minutes. But essentially, the way to read it is there are 4 key rows and 4 transition states. And the bottom row essentially captures a reality that's created when light's traveling at a constant speed of c. And then the rest are hypothetical. It's a hypothetical model of light. The top row is reality that's created when light's traveling infinitely fast. And so let's dive into it a little bit more. What do each of these rows mean, and how does quanta emerge from such a model of light? So if you consider light traveling at c, so c is the speed that we have physically proven light to exist at in our universe. And a very simple thought experiment to understand the reality that would be created when light travels at c is to imagine light coming from the sun. It takes 8.5 minutes to get from the sun to the earth. So if you're in the middle of that journey, about 4 minutes in that journey, and you imagine you're on a light ray, then 4 minutes in the past, you were at the sun. 4 minutes in the future, you're going to be the earth. So the concept of time is really emergent from this finite speed of light. So we can say that the concept of past, present, and future really emerges because light is traveling at a finite speed. Now, if light were traveling infinitely fast, there would be no past, present, and future because all time would just be happening now. A fourth property is that when light travels slower, there's an accumulation of energy. And because of that accumulation of energy, that allows matter to form. And that's the basis of Planck's constant, which I'll get into in a couple of minutes. So we can see that 4 very fundamental aspects of reality that we experience are due to light traveling at a finite speed. Now, we have to ask the question, what does the past, present, and future and matter really represent? And that gets to the bottom layer of this model or representation of light. So in the past, so as we look around in this room, everything that exists is a result of the past. So there's a status quo, there's a physicality to the essence of the past, and that's why the past is really, I represent it as something that I call physicality, which is just represented by P. The present is a play of forces. So right now, in this very instant, there's a whole bunch of thoughts, emotions, assumptions that are going through each of our minds, or collectively as a group. And it's only the strongest expression that's going to emerge. And so, in a sense, the present is a play of force. So that's why it's represented as vitality. And then when we think about the future, there's an inevitability. So certain ideas are going to inevitably become real. And so there's a causality and a mentality. So the future, this notion of the future is represented by M, which is mentality. And then matter, the arising of matter allows basically connection between these different seemingly isolated elements that have emerged in this universe created by light traveling at c. So we have 4 properties that emerge when light travels at c. And again, there's a lot more detail in the paper, so I've just gone through this very quickly. Now let's move to light traveling infinitely fast. And here we can say that if light were traveling, let's imagine a globe. And the globe can be as large as the galaxy or universe, planet Earth, however large we want to make it. And imagine a light source at the center. Now, if light's traveling infinitely fast, then that light is going to be present all over this globe instantaneously. So it's going to have an omnipresence. It's going to be present everywhere. Since that light is present everywhere, it's going to know what's rising up and what's disappearing. So it's going to have a knowledge of that space, an intimate knowledge of that space. So it has a property that I would call omniscience, or all knowledge. If there's anything not the nature of light arising in that space, sooner or later it's going to be overcome by the nature of light. And so light has an omnipotence or an all power to it. And then similarly, because light connects everything instantaneously in that globe, there's an aspect of harmony because everything is connected in the nature of light. So we can see that there are four fundamental properties that emerge when we consider light traveling infinitely fast. And these, just mathematically, I represent these as presence, power, knowledge, and harmony. And that's the top layer. So we have these, something that we call, for example, let me just elaborate on this thing called knowledge. Imagine you have something called knowledge. So knowledge may be, the way that we represent knowledge may be a set of infinite elements that basically have slight differentiation between different aspects of knowledge. So knowledge could be wanting to seek knowledge, wanting to gain knowledge, wanting to spread laws of knowledge. There could be a number of things, or just setting into motion laws that are knowledgeable. So there's an infinite number of elements around what knowledge could represent. Now, when we look at this set, this from the top to the bottom, and we know that in our reality there's infinite diversity, it's material and it's infinite diversity, the question is, how does these four properties become infinite diversity? And it can through a mathematical transformation, a couple of mathematical transformations. So the first transformation is where you basically elaborate each of these concepts, presence, power, knowledge, and harmony, into larger sets. And that's what this layer is about. And then you take each of these these sets, so you have four large sets, and you create unique elements that are combinations of elements from these sets. And so you can come up with infinitely diverse seed elements. And these seeds can become the basis of this material expression that we experience here in the material universe. So that's the basis of this, in just a few minutes, the basis of this model of light, where you have four properties becoming infinite diversity through two mathematical transformations that are taking place. And that's what this essential model of light is trying to capture. Now the question is, when you think about quanta in such a model, and the reason why I think we need to think about quanta more deeply and quantum computation is because we're spending billions of dollars on creating computers and assuming that quanta work a certain way and that reality at the quantum level is basically typified by phenomena we call superposition and entanglement, but we don't have any deeper understanding of what these really are. So at this point, I think it's premature to spend billions of dollars, but we need to do some more research on some basics and fundamentals. And so what this paper is trying to do is just challenge the existing position to say, okay, what are alternative models of quanta, and therefore how can we alternatively think about quantum computing as a result? Now, in this model, what I would position quanta to be is basically a device that takes information at a faster moving layer of light and materializes it in a slow moving layer of light. So quanta exists to materialize information that exists in possibility. So even when we think about quanta, if there's physicists over here or people who've looked into it in some detail, the quanta really is, when the black body experiment was performed, which is how Max Planck came up with the notion of quanta, when you heat a black body, it won't go through a continuous shift in color. There'll be discrete jumps. And so that kind of is how he came up with the notion of quanta. So the idea being that there's information collected, and when a certain threshold of information is collected, then it expresses itself in something that we can understand. So it materializes information in a concrete way, and that's how I would think about quanta. So in this scheme, there would be various quantization functions, and we can approximately think of quanta as something that materializes at this layer of reality, but it has a lot of dynamics going on behind it. And mathematically, we can also arrive at a similar conclusion. So there's some fundamental equations. For example, the first one, that when you shine a light at say an atom, earlier it was thought that, or at a metal, that the intensity of the light would dislodge electrons in the outer shells of an atom. But in fact, it's not the intensity, it's the frequency of the light. And so a blue light will dislodge more electrons than a red light, for instance. So E equal to hv is essentially just capturing that notion that you have a quantum relationship between the energy and the frequency of the light, and it's captured by Planck's constant. The second equation is the speed of light, which is a constant, and so therefore you have infinite variation in frequency and wavelength. And when you combine those two equations together, for a fixed energy, you can see that C and H are inversely proportional. And so hypothetically, if you increase the speed of light, suppose light can go up to a speed way beyond C, then H would have to diminish to maintain that equality. And because H diminishes, therefore matter wouldn't be able to form, and you would have a wave, or you would have a field, or you would have a block or something else happening instead. And so you can kind of get to a notion of that there is perhaps other layers of a reality when when you vary speed and H, if that's possible. So in this model, basically quantum computation or quantum levels are not probabilistic, but there's some kind of determination to them, and this determination needs to be worked out. Because right now, our models of quantum computing are based on, basically are probabilistic. They're assuming that reality is probabilistic, and therefore that quantum computers are also probabilistic in nature. So that makes a case, just even if we look at these basic equations, that we need to rethink how we're thinking about quantum computing. Superposition. So Copenhagen interpretation of quantum computing says that at the quantum level, a quantum object can be an infinite number of states, and only when we begin to measure, it'll collapse into some state. But if we look at this model, what we're basically saying is that superposition, you could have an entity that shows up at this layer of reality, but it has different simultaneous representations if you think about light moving faster. So that's how superposition would work in this model. Entanglement, which is another key concept in quantum computing, would work differently as well, because in this model, everything is by nature already entangled at an infinite speed. It's intimately entangled. And so we have to ask the question, what does that really imply when you think of a larger system where everything is already intimately entangled? When we think about the dual slit experiment, which is a key experiment which has led to the notion of superposition, an alternative explanation for that is the de Broglie-Bohm pilot wave explanation, which says that there's a wave reality that exists, and depending on how waves interfere, particles will show up in those areas. So it's assuming a different explanation than the fact that it's completely non-determinable. So we're saying it's deterministic, but in a different way. And then finally, one of the things to consider is that I believe we're asking the wrong questions with current models of quantum computing, because in the current models of quantum computing, we're trying to compute faster what we do digitally. But in reality, if we think about the quantum layer to me is fundamentally creative, because that's where reality emerges. And so I would argue that a quantum computer could be very creative rather than constructive. So it's a different paradigm altogether. So in terms of further research, I think there's a lot of avenues for further research to just think about what really are quanta, how do they function, what really is superposition, what is entanglement. I didn't talk about aggregation, statistical aggregation, but in probability, basically what we assume is that there's a lot of probabilistic phenomena, and then when you aggregate, it kind of becomes a law. But I would flip it around and say that there's a function that exists at a meta level, and when you statistically disaggregate it, it becomes the apparent randomness that we see. So there's another way to think about statistics and probability that we also need to look at in more detail. And then what I mentioned just before this slide was that if the quantum level is really about innate creativity, then the question is, how do we manipulate that creativity? So we're trying to solve the wrong problem with our current approach to quantum computing. So I think these are all areas of research. Questions? Yes.
Half my question at this point of view, but my knowledge in quantum computing is a little bit limited. But my question is, how are you going to do, or how the speed of light will be faster? I mean, I would make sense of the rest of.
Sure. So I think that, of course, there's some thinkers already say that, thought travels faster than the speed of light, for instance. Or even in quantum, when you look at this phenomena of quantum weirdness, where when you entangle two photons together and you separate them miles and miles, then you make a change to one photon, it'll automatically reflect in the other photon. It's not possible for it to happen instantaneously, yet it happens instantaneously, which means that somehow something is traveling faster than light. So, the basis, our assumption that light is an upper limit of travel, I would say is incomplete. It's flawed, because things can travel faster than light. We just haven't physically proven that yet. So.